Hello everyone, this is Zhongyi. I'm gonna present the paper written by me and Robin Evans, faster algorithm for Markov equivalence. So I begin with a summary of our main results. First, we give a new non-parametric graphical criterion of Markov equivalence between maximal ancestral graphs, and based on the criterion, we provide a fast algorithm for verifying equivalence between two max. And also we gave fast algorithm for transferring an ADMG to a equivalent MAC. So I'll give an introduction to graphical model. So DAGs, directed acyclic graphs, which are also known as Bayesian networks, are popular graphical models that are often used in many fields, like estimating causal effect or pattern recognition in machine learning. A DAG encodes conditional invariance by pass criterion called deseparation. So for example, for the two graphs here, they represent the same distribution, which has a conditional independence where 1 is independent of 4 given 2 and 3. And such graphs with the same conditional independence are said to be Markov equivalent. There's a theorem states that two DAGs are equivalent if and only if they have the same adjacencies and unshielded collider. However, this problem with DAG, it is not closed under marginalization. So consider the figure below, where h is a hidden variable. Then there is no DAG that describes the conditional independence on the marginal 1, 2, 3, and 4 precisely. And a solution to that is acyclic directed mixed graph ADMG, which has an additional type of edge, bidirected edges. And there is a subclass of ADMG, maximal ancestral graphs, introduced by Richardson. And in that paper, they gave advantages of MAG and also provide a projection that can convert a DAG or ADMG to an equivalent MAG given the latent variables. So one simple example are the figure below. So these two graphs are equivalent, and for the second one, it is a MAG. So there have been three graphical criteria which use the following to categorize a MAG: discriminating paths, minimal collider paths, and colliders with order. And only the last one provide a polynomial time algorithm. And the new criterion in our paper leads to a faster algorithm, and also it holds true for ADMGs. So the reason we study the criterion of the equivalence between two graphs is, firstly, we can understand the graph better, and also it is essential for structured learning because we can never distinguish two graphs in the same equivalence class without any further assumption if we just use independence test. So in our criterion, we use heads and tails that arise in discrete parameterization of graphical model. A head is a set of vertices satisfying certain properties, and for each head, there is a corresponding tail. We won't go through the definition of heads and tails as they are quite long. The intuition for defining heads is that for head H, there is no independence in a head without marginalizing some elements of H, and further we show that it is true if we include any subset of tail. Let Hg be the set of all heads, and we define the parameterization set as all the set in form H union with A, where A is a subset of tail of H. We also consider S3 and S3. The first one contains the set in S with size less than or equal to 3, and for the second one, we exclude the set in S3 that has full adjacency or no adjacencies. So let's take a look at these three graphs and their corresponding S and S tilde 3. For the first two graphs, they have the same S and S tilde 3, and indeed they are Markov equivalent. So for the first two graphs, we can see that for S tilde 3, we exclude 1, 2, 3, and 2, 3, 4 in S because these two triples are of full adjacencies. So our main result is theorem 3.2. It states that two mags are equivalent if and only if they agree on the parameterization set S, or they agree on S3, or they agree on S tilde 3. And let's take a look at the proof of one direction of our theorem. So proposition 3.3 says that for a vertex set W, It is not in the parameterization set if and only if we can M-separate two vertices A, B, and W, given a superset of the remaining vertices in W. So with this proposition, one can easily see that one direction of the theorem holds. So if two graphs are equivalent, then they represent the same conditional intervals, and hence they should have the same parameterization set. And based on the theorem, we provide an algorithm for computing S tilde 3 of a given MAC-G. We simply need to compute tails of every single vertex, which are their parents, the tails of every head of size 2, and every head of size 3 in S tilde 3. And note that in a MAC, a set of size 2 is a head if and only if they are connected by a bidirected edge. The mean contribution on complexity comes from the third term, and we show that the overall complexity is upper bounded by n squared, where n is the number of vertices and e is the number of edges. And we also show that under a certain type of Schwarz graph model, where each edge has an IID Bernoulli distribution, the expected complexity is at e squared. So the intuition behind this is that we can bound the expected number of ancestors of each vertex, so we can verify if a set is a head in a constant time. Further, one of advantages of our criterion is that if we consider S3, which can be gained at polynomial time, it is a summary of independent information in that graph. So if we know a set ABC is in S3 and AC are not adjacent, then we know that there is no invariance between A and C given any subset containing B. We also show that heads or tails are preserved through the projection from ADMG to MAC. So the theorem is extended to ADMG. Also, we can verify equivalence between two ADMGs in polynomial time. And at last, the graph so far we talk about does not contain any undirected edges, but it is straightforward to extend to max and ADMGs with undirected components on top by considering cliques in the undirected components. So that's the reference I use in the slides, and I think that's all. Thank you.